Hello, everyone. I'm Xinpeng Liu, presenting Scaled Mouse, an efficient and accurate interaction technique for 3D docking in seated VR, joint work with Zhao and Wolfgang Stuerzlinger. Today, I'll show why a regular mouse can be a strong alternative to VR controllers for accurate 3D manipulation in seated VR, especially for rotation and docking tasks. Seated VR is common in offices and living rooms, but switching between headset controllers and desktop devices disrupts workflow. Controllers also often lack the precision needed for fine manipulation, and they impose a learning curve. Meanwhile, the mouse is familiar, stable, and desk-supported, and prior work has shown it can outperform specialized 3D devices for some 3D tasks. Our question is, can we adapt a standard mouse to support full 6 degree of freedom manipulation in seated VR, efficiently and accurately? Our technique, Scaled Mouse, places a virtual mouse model in VR aligned to the real mouse on the desk, then uses it to drive a ray cursor for selection and manipulation. The goal is a hybrid workflow. Keep your hand on the mouse, use ray-based selection for distant objects, and get stable, precise control during manipulation. First, we show the mouse in VR using a new technique. We initialize the mouse position by using headset hand tracking via OpenXR to obtain the 3D pose of the hand holding the mouse. When the user briefly moves the physical mouse and motion is detected, we align a virtual mouse model under the user's hand. This establishes a correspondence between the physical mouse and the virtual mouse in VR. After initialization, a virtual ray extends from the tip of the virtual mouse. Horizontal mouse motion rotates the ray left and right, and vertical motion rotates it up and down. A white sphere indicates the 3D cursor. Left click selects the object under the ray, and we outline it as feedback. To keep interaction stable, small head motions do not disturb the ray. But if the head rotates relative to the ray beyond an asymmetric yaw threshold for more than 2 seconds, we recenter the ray to the new field of view, minus 70 degrees left, plus 45 degrees right, swapped for left-handed users. Users can also press the middle mouse button to recenter instantly. We interpret mouse input as a continuous control signal for ray orientation. Per-frame mouse axis values are integrated over time, so the ray updates are frame rate independent. In short, mouse motion increments yaw and pitch over time, and we clamp it to remain comfortable in view. After selection, we map standard mouse actions to 6 degree of freedom manipulation. The key point is, we can do full translation and rotation using clicks, drags, and the wheel, similar in spirit to what controllers provide, without extra refinement modes. This is the practical feel of the system. Keep your hands supported on the desk, and use familiar mouse gestures for precise control. Our first user study compared 3 techniques: controller-based direct manipulation, controller-based joystick manipulation, and mouse-based manipulation. Participants performed 3 task types: position only, rotation only, and combined position plus rotation docking. We measured completion time and final position and rotation errors. The main outcome is consistent. The mouse achieves higher accuracy, especially for rotation and docking tasks. Errors are consistently smaller when using the mouse. For rotation in particular, the difference shows a large effect size, as reported in the paper. Participants also preferred the mouse. It scored highest on perceived ease of use, with a median of 4 out of 5, compared to joystick 3.5 and controller 2. We also measured usability for the mouse system using SUS. The mouse system scored 78.1 on average, significantly above the benchmark of 68. So, Study 1 suggests, in seated VR tasks that demand precision, a familiar mouse can outperform controllers, particularly for rotation and fine alignment. Study 1 also revealed a limitation. The mouse wheel produces fixed increments, and participants struggled with depth manipulation at larger distances, especially when tasks needed both large moves and fine corrections. So, in Study 2, we introduced velocity-based scaling for the mouse wheel, inspired by the principle behind scaled Homer. Fast input gives coarse movement, slow input gives fine control. Study 2 compares scaled mouse against scaled Homer and adds an optional 2D adjustment panel that shows numerical pose differences in sliders, mimicking productivity tools. We also tested different panel sizes, because interface scale might change how people use the panel. In Study 2, scaled mouse again performs strongly, especially for rotation and combined docking tasks. For rotation tasks, it is significantly faster, averaging 24.2 seconds compared to 31.6 seconds for scaled Homer. For combined position and rotation tasks, scaled mouse produces significantly smaller errors and is also significantly faster, averaging 33.6 seconds versus 47.7 seconds. Subjective measures also strongly favor the mouse. SUS for scaled mouse is 85.3, and workload is much lower. NASATLX overall 7.38 versus 13.55, with large effect size. A key interpretation is stability in the fine adjustment phase. In this plot, scaled mouse is shown in orange and scaled Homer in blue. In the paper's time series analysis, the scaled mouse shows smoother trajectories and narrower confidence intervals for much of the task. The advantage becomes particularly clear during the fine adjustment phase, especially for rotation. Also, the auxiliary panel tended to act as a fallback more for the controller, while mouse users often didn't need it as much, consistent with higher direct manipulation precision. To conclude, scaled mouse shows that a conventional mouse, carefully adapted, can be efficient, accurate, and usable for seated VR manipulation and docking, especially where rotation precision matters. Our contributions are threefold: a seated VR system that visually shows the real mouse in VR, aligned with the tracked hand, enabling users to easily reacquire the mouse, together with robust ray control and recentering. Evidence from 2 user studies showing competitive and often superior accuracy and usability versus controller baselines, and velocity-based scaling and optional panel support to transition smoothly between coarse and fine adjustments. Future work includes long-term ergonomics and fatigue, and combining mouse input with gaze or voice for productivity workflows.